Hello everyone. Welcome to Analog Electronic Circuits, lecture number 13, part number 2. So in today's lecture, we will analyze the common emitter RC coupled cascade amplifier, right? So the circuit in front of your screens is a common emitter cascade amplifier. This stage over here is my first stage. So let me mark it. So I'll keep it over here. Let me bifurcate this. This is my source as we have discussed in the single stage amplifier. So this will mark call it as source. This is my first stage, and then in series with the cascade we have the second stage. So this is the second stage. And at the output we have a load. So let me put a bifurcation over here. So this is the load part, and that is my second stage. Okay, so the advantage of a cascade amplifier is that let's say that the first stage gain is around 100 and the second stage gain is around 50. For a normal common emitter amplifier to achieve such gain is not impossible, right? So what will be the overall stage for a cascaded stage? The total gain, voltage gain will be of a cascade amplifier will be AV1 into AV2, and that will be 100 into 50, and that comes out to be the total gain comes out to be approximately equal to 5000. So such a high gain is possible in a cascade amplifier, common emitter cascade amplifier. So that's the advantage of a common emitter RC coupled cascade amplifier. Fine. So it provides a very high gain. Fine. So for this analysis purpose of RC coupled cascade amplifier, now why it is called as RC coupled? Because if you see carefully, the output of the first stage is connected to the input of the second stage via this coupling capacitor. Okay, so this is the capacitor, and where is my the R which is coming? The R will be the input impedance of the second stage, and over here input impedance of the second stage over here will be R3 parallel to R4 parallel to R pi 2, right? So that will form the RC coupling. Fine. Now let's move forward, and for this we have a goal for analysis purpose. We have to find our goal is to estimate input impedance R in, output impedance R out, and the voltage gain AV. So for a cascade amplifier, for all the cascade amplifier, we have to find these three. So this Rn is called as input resistance or input impedance, we call it. Okay. Then R out is nothing but my output resistance, and AV is my overall voltage gain of the cascade stage. Okay. Okay. So to find these three quantities, we have to draw the mid frequency equivalent circuit. Okay. So next is we will draw mid frequency small signal, mid frequency small signal equivalent circuit for the above cascade amplifier. Okay. So we will draw that now next quickly. Okay, fine. So to draw the mid frequency equivalent circuit, there are certain conditions. The conditions are that we have to short circuit DC supply and short circuit all the connected capacitors. So we have to short circuit all the connected capacitors. So that's the assumption for drawing the mid frequency small signal equivalent circuit. Okay. So first of all, what we will do is we'll replace the BJT Q1 and Q2 with its hybrid pi model. So over here we will also write next step will be replace BJTs with its hybrid PAM model. Okay, so let's draw the hybrid PAM model of both the BJTs first, and then we will proceed. Fine. Let me slightly increase. Yeah. So first of all, I will draw the hybrid PAM model for Q1 and Q2 separately, right? And mark base 1, collector 1, emitter 1, base 2, collector 2, emitter 2. Fine. So let's proceed. So first of all, I will draw the hybrid PAM model for the for Q1 transistor. So here we have base 1, collector 1, and emitter 1. We'll write it over here. This is base 1, collector 1, emitter 1. Similarly, over here, we'll leave some space and write it over here. This is base 2, collector 2, emitter 2. Okay, now we'll complete the hybrid PAM model. Between base and emitter, we have R pi resistance. Okay, we call it R pi 1. And the voltage across this is V pi 1. That's the hybrid PAM model. And over here, we'll have a current source GM1, V pi 1, and also we have RO1 present over here. Okay, so this completes the hybrid pi model for the Q1 transistor. Similarly, we'll complete it for the Q2 transistor. Here we'll have R pi 2. Why? Because we'll have two stages. That's why we cannot call them R pi together. So I'll call it as R pi 2. And this will voltage will be V pi 2. The between the collector and the emitter, we'll have a voltage dependent current source. We can call it as GM2 into V pi 2, and also we can mark over here RO. Okay, so hybrid PAM model was covered in the previous lectures, so I'm not repeating that again. Okay, okay, now we have to join them together and one by one. So let's start with base 1 terminal. Okay, so over here, what is connected between base 1? So base 1 will have R1 and R2. Now R1 other end is connected to the ground, R2 other end is connected to the ground. So R1 and R2 will come in parallel. And then we have this capacitor will be short circuit. Then we have RC and VS. Okay, so we'll mark that over here. Fine. So over here on this side, from the base side, we have RC over here. And then we have R1 parallel to R2. Okay, sorry for that. Here we can write R1 parallel to R2. Here we have in series R6, and we have a voltage source Vs. This is a voltage source Vs plus minus. Fine. So the base one is clear. Now we'll go to emitter 1. So if you see carefully, emitter 1 we have resistor Re. In parallel we have a capacitor, and capacitors we are short circuiting it. Okay. So emitter 1 will be going to the ground. So let's mark emitter 1 and note it goes to the ground terminal. Okay. Now let's see what is connected between collector 1 and base 2. Okay. From the collector 1 side. So from the collector 1, we have RC1 connected, and it's going towards the ground because VCC is grounded for mid-frequency small signal model equivalent circuit. Then this capacitor CC2 will be short circuited. So collector 1 terminal will be connected to base 2, correct? And then from base 2, we have R3 parallel to R4. Fine. So let's draw that. From collector 1, first of all, we will have a resistor which is RC1, and then collector 1 is connected to base 2, and from base 2 we have a resistor which is called as R3 parallel to R4. Okay, so that is what we have so far. Now let's go to emitter 2. So emitter 2, again we have RE2 connected in parallel with CE2, and CE2 is short circuited. So emitter 2 will be going towards the ground. So from here we'll have emitter 2 going towards the ground. Now only thing left is C2, that is collector 2. So from collector 2 we have resistor RC2 which is going towards the ground, and then CC2 is short circuited. RL is also going towards the ground. So RC2 in parallel with RL. So over here we'll have from the collector to the here we'll have RC2 connected towards the ground, and then finally we have RL, which is also connected to the ground, and in parallel we have can show the voltage plus minus V out. Okay, fine. So this is how your mid frequency small signal equivalent circuit will look like. Now let me mark where are the AC voltages in the circuit. So over here, this output is containing AC component. This VCC is DC, and this VS is my again a small signal AC component. Fine. Now similarly over here, in the mid frequency small signal equivalent circuit, it represents only AC quantities, small signal time varying quantities. So basically, whenever we draw a hybrid pi model for a BJT, right, we are linearizing the non-linear BJT, provided that the input is small signal, correct? And now next we have to analyze the circuit and find out R in, R out, and the voltage gain. So let's proceed forward from here. Okay. So first of all, we'll find out the input impedance. So remember input impedance in case of your cascade stage. First, let me write down over here. First, we'll find out input resistance, expression for input resistance. So input resistance is denoted by R in. Okay. So let's find out input resistance. So input resistance will be looking into this terminal over here. This is Ri. This is input resistance of the amplifier, right? And there is one more. This is called as R in. This is the input resistance of the circuit, correct? So this is the amplifier and this is the circuit. So from here, let me also mark certain things before going forward. Okay, let me mark the stages over here, right? So here this will be my source. Okay, this will be my source terminal. My source side, voltage source. This is my first stage, and over here it completes. And here we have a second stage, and from here to here, and then we have RL, and this is my load. Okay, so it's very important to identify them so that we correctly determine the parameters. Okay, so we have to find Ri and Rn. So Ri will be like if we are standing over here. So what do you see on the right hand side? We see R1 parallel to R2, and again we see R pi 1. Okay, we stop over there because the impedance offered by the current source Gm into V pi 1 will be infinite. So what will be Ri first? We'll write it down. Ri will be equal to R1 parallel to R2 parallel to R pi 1. Okay, and what will be Rn? So basically it's looking like this now. Let me redraw the circuit now. So we have R sig, and here we have Ri, and here we have the voltage source. Okay, now the input side looks something like this. So what will be the resistance looking from here? This Rn. So this Rn will be R6 plus Ri. Simple, they are in series. So that is what we will write next. So Rn will be equal to Ri plus R6. Okay, so that becomes my input impedance of the circuit. And also there is one fact, there is one concept that the input impedance, let me write over here, the input impedance of a cascade stage will be equal to the input impedance of the first stage. Okay, so this actually this is true over here. The input impedance Ri, which is R1 parallel to R2 parallel to R pi 1, is the input impedance of the first stage. Fine. So this concept you please remember. Now let's move on to the output impedance. Okay. So let's say we want to find output impedance looking at the load side. So this is my R out. Fine. So R out, if you stand over here, if you look towards the left, what you will see? You will see RL parallel to RC2 parallel to RO2, and that's it. Why? Because impedance offered by this current source will be infinite, GM2 into V pi 2, right? So R out will be RO2 parallel to RC2 parallel to RL. So that is what we write. And output resistance is basically the output resistance of the last stage. That's the funda which we have learned last time. Okay. So now let's write it down formally. Output resistance. Okay. So output resistance is R out. So what have we calculated here? R out is RO2, small RO2 parallel to RC2 parallel to RL. So we'll write it exactly as it is. So R out will be equal to RO2 parallel to RC parallel to RL. So in this manner, we calculate the value of output resistance of the cascade circuit. And what was that concept which we have learned? That the output resistance in a cascade stage will be equal to the output resistance of the last stage. And in fact, there are two stages over here. The output resistance is in fact equal to the output resistance of the last stage itself over here, if you see carefully. Fine. Is this clear? Okay. So let's move on now. Let's move on to the next point. Now, next, we will find the values of, we will find the expression of voltage gain. Okay. We'll find the expression of voltage gain. Now, for that, let me just, copy this circuit again. Okay. Give me a minute. We are supposed to find the value of voltage gain, expression for voltage gain. So let me just add this below again. Okay. So that we have a fresh circuit with us. Okay, fine. So now we are supposed to find the voltage gain. Yeah, I think it is clear now. So what is voltage gain over here? Voltage gain, our voltage gain will be given by the output voltage divided by the input voltage, that is Vs, V out upon Vs. But we have two stages, right? So the voltage gain also will be like individual voltage gain we'll want to we wish to find out. So over here, what do we do is we'll just mark one more quantity over here, variable. We call that variable as V1. Okay, and that is going to the ground. We called it as V1. So what is V1? V1 is the output of the first stage and input of the second stage, right? Now, if I want to write the gain of the second stage, how will I write? V out upon V1. Okay. So here AV2 gain of second stage will be V out upon V1. What will be the gain of first stage? So I'll write AV1 is equal to V1 is the output of the first stage, and V in, here I'll mark V in over here, this plus minus V in. I mean, let me add R1 parallel to R2 a little down this side. Oh, sorry. This is R1 parallel to R2, and this plus minus, this is V in, the voltage in parallel, right? Because V in and Vs are not same. They differ by, we have Rsig in between. If Rsig is 0, then Vs and V in are same, right? So the gain of second stage will be V1 divided by V in. What about V in and Vs? Between V in and Vs, we have a voltage division. Okay. So we have to find out that voltage division, what it is. So I can redraw this part of the circuit, right? So over here, we can write it as follows. So I'm redrawing that part. Here we have R sig, and here I have Ri actually we can write, because you're representing Ri only. So this is Ri, and this is my voltage source Vs, plus minus, and that's going to the ground. And we are supposed to find this voltage, which is V in. So we can use a simple voltage division rule. So what will be the answer over here? Okay, let us write it down. V in upon Vs. So V in will be written as V in will be equal to Ri divided by Ri plus R sig into Vs. So we have the relation between V in and Vs. So now we can write this AV voltage gain, overall voltage gain as follows. It will can be written as V out upon V1, V1 upon V in, and V in upon Vs. So from here, we can easily determine that the first quantity is the gain of the second stage, the second quantity is the gain of the first stage, and the third quantity is given by Ri divided by Ri plus R6. Okay, so that's the overall voltage gain of the circuit, correct? And now we can write it in this form that overall voltage gain AV will be given by AV1 into AV2 into Ri divided by Ri plus R6. Okay, clear it is? So next we have to determine the expression of AV1 and AV2. Fine. So let's start and find out the expression of AV1 and AV2. Fine. So now we know that AV2 is basically given by V out upon V1. Okay. So we can write over here AV2 is basically V out upon V1. Now, if you see carefully, what is V out? Over here, we have a parallel voltage V out and we have a three resistance over here, right? So these three resistances over here, let me just highlight it, right? These three resistances are in parallel, okay? So I can write V out is equal to, these three resistances are called as R out, okay? R out is RO2 parallel to RC2 parallel to RL. Fine. And this resistance into this current. And what is this current basically? This current is nothing but IC2. And this current is outgoing current. Okay, it's moving out of the terminal. It's not moving into the ground. So I can write here V out is given by, I mean, let me use a black color. Yeah, let me write, okay, fine. Let me select a black pen. So V out is equal to, I can write V is equal to IR, right? And these three resistances are in parallel. So I can write, and they are equal to R out. So I can write V out is equal to minus IC2 into R out, where R out is RO2 parallel to RC2 parallel to RL. Let me write that, where R out, it's basically equal to RO2 parallel to RC2 parallel to RL. Fine. And what is IC2? IC2 is basically equal to, IC2 is nothing but GM2 into V pi 2. And what is V pi 2 from here? What is V pi 2 from here? V pi 2, if you see carefully, V pi 2 is same as V1 because they are in parallel. So V pi 2 is equal to V1. And now if I rewrite the expression of V out, I'll get V out is equal to minus of IC2 is GM2 and V pi 2 is V1. So GM2 V1 into R out. I can expand that R out later, but that is what we have so far. So now I can write, actually AV2 is V out upon V1. So I can write AV2, that is AV2 is V out upon V1, right, is equal to minus GM2 into R out. And what is R out? RO2 parallel to RC2 parallel to RL. So this is my expression for, this is the expression for the gain of the second stage. Okay. So this is gain of second stage. Always find out the gain expression for the second stage first, and then you can move on. Okay. So that's an important relation, and that is what we have. DC resistances were in parallel. Okay. Now this is over. So very good. So we have found out the value of the gain of the second stage. Now let's move on our attention to AV1. Okay, so AV1 will come over here. AV1 is the gain of the AV1 is the gain of the first stage. So let us start writing over here. AV1 will be V1 divided by V in. Okay, so let's concentrate over here a bit. Let me just expand it slightly. Yeah. Okay. Now what is V1? V1 is over here. And how many resistance do you see over here along with V1 in parallel? R01, RC1, R3, parallel to R4, and then parallel to R pi 2. Correct? So these many resistances are in parallel. So let me mark it with a green color, right? So these resistances are okay. So these many resistances are in, let me just mark it thoroughly. So these many resistances are in parallel with each other, correct? So these resistances into the current. And what is the current flow over here? The current flow over here is IC1. Again, it is an outgoing current. So how can we write over here? What can we write over here? A V1 is equal to, let me take it this side a little. Okay. So I can write V1 is equal to minus of IC1 into these many resistances. Okay, total 5 resistance in parallel. R01 parallel to RC1, parallel to R3, parallel to R4, parallel to R pi 2. Okay, so we'll write it systematically over here. So it will be a V1. Let me rewrite it. V1 will be equal to minus IC1 into R01 parallel to RC1 parallel to R3 parallel to R4 parallel to R pi 2. Okay, and that is what we have representing over here. See these 5 resistances R01, RC1, R3, R4, and R pi 2. These all are in parallel. Now what is IC1 from this diagram? It is GM into V pi 1, right? So let's write that IC1 is equal to GM1 into V pi 1. Okay. And what is your value of V pi 1? Your V pi 1, if you see carefully, V pi 1 is in parallel with V in. They are in parallel. So that we can write V pi 1 is equal to V in. So now if I want to write V1, I can write that is V1 is equal to minus of uh, instead of IC1, I'll write GM1 into V pi 1. Instead of V pi 1, I'll write V in. And I'll write all the 5 resistances which are there over here. R R01 parallel to RC1, parallel to R3, parallel to R4, parallel to R pi 2. Okay. And now we know that AV1 is V1 upon V in. So we can write easily that is AV1, which is equal to V1 upon V in, is equal to minus of GM1 into those 5 resistances in parallel. R4 parallel to R pi 2. Let me write R pi 2 thoroughly. Okay. R4 parallel to R pi 2. Okay. So I'll put it inside the bracket and this becomes the expression for the gain expression for the first stage. So this is my gain of, this is the expression for the gain of first stage. Okay, fine. So yeah, we have found out the expression for the gain of the first stage, and we are already found out the gain of the second stage, right? And yeah, let me show it to you. This is the gain of the second stage AV2, and that is the gain of the first stage over here. Okay, let me mark it with green color so that I can highlight that these factors are representing the first stage and the second stage respectively. Okay, fine. I hope that you all don't have any doubt over now here now. So we have found out the expression for the gain of expression for the first stage gain and the second stage gain, right? So now we can write down. I mean, if you have the expression for AV1 and AV2, and we know the value of Ri and R6, we can calculate the overall voltage gain AV for the circuit, right? And that is given by this formula over here. So once we know the value of AV1, once AV2 is known, Ri and R6 is known, we can easily calculate the overall voltage gain of the cascade amplifier. So here this is overall voltage gain of CECE cascade amplifier. CECE cascade stage. Okay, fine. So we have found out the expression for the voltage gain. Then we have found out the expression for the input resistance and output resistance for this. Let me go back to the diagram. For this common emitter RC coupled cascade amplifier. Okay, which consisted of two single stage RC, two single stage BJT amplifiers connected in a cascade form. Cascade meaning connected in series. Okay, so let me add it over here. What is the meaning of this cascade? Cascade means connected in series. The transistors are connected in series. Okay, fine. So that's the analysis of common emitter RC coupled cascade amplifier. In exam, if they ask you to derive the expression for input impedance, output impedance, and the voltage gain expression for a cascade amplifier, you have to do it in this manner. Fine. Yeah, so we have come to the end of this session, and we have analyzed the common emitter RC coupled cascade amplifier. And in the process, we have drawn the mid frequency small signal equivalent circuit. From that, we have analyzed derived the expression for input impedance, output impedance, and finally the overall voltage gain of the cascade stage. Okay, so I think that's all for this session. Next time, we'll solve a numerical on the on this cascade amplifier stage, that is common emitter RC coupled cascade stage. So until then, have a good day and thank you.